Okay, here we are back again at what used to be my dining room table, and I'm going to try to work on lab20 part 2, which is the cmos push-pull. It's actually very easy to do in Circuit Lab, but I built it here. I'm using +5, that's the red wire, and -5, that's the white wire from the Digital and Analog Discovery 2 board. And then I have one of the black ground wires going here in the bottom row, and I have one of the black ground wires going here on the top row. So I have +5, ground, ground, -5. And then if I want to, I can replace the 5 volts plus and -5 with plus and -9 using a pair of 9-volt batteries. But for now, let's use the 5 volts. And then I built the circuit as indicated here. So this is the same NMOS transistor, the RFP50N06 we used in part 1. And then this FQP47P06 is a PMOS MOSFET transistor that, so an NMOS and PMOS combination is analogous to an NPN PNP combination. So it looks like the familiar push-pull. So this yellow wire is the signal generator from the Analog Discovery board. There's a 1K resistor, and that's going into the gate of the N-channel MOSFET. That gate is just wired over with this little blue jumper wire to the gate of the P-channel MOSFET. So I have gate, drain, source for N-channel, and then I have gate, drain, source from right to left. So that's source, drain, gate for the P-channel. So I had to reverse one of them. So the NMOS is going the standard way, gate, drain, source, and then I flipped the PMOS upside down. So instead of left to right, it's going right to left, gate, drain, source. So then the two sources directly connect to each other. That forms the output. You might wonder why I'm using as few wires as possible, because I'm cutting wires off of little 9-volt battery holders, because I actually shipped my last spool of breadboard wire to a student with a kit. So I have more breadboard wire arriving from Amazon on Friday also. Anyway, then the orange wire is probe channel 1, so it's looking at the two gates. So it's looking right here on the schematic. And then the blue wire is channel 2 of the oscilloscope. So it's looking at the two sources. So that's this point on the schematics, that's the output. There's a 1K load to ground. And then if we look up on the scope display, well, here I can show you what I'm putting in first. So if I go to wave gen, then this is a 5-volt amplitude, which means 10 volts peak to peak, sine wave at 1 kilohertz. And then we'll go over to scope, and you can see it looks kind of like a familiar push-pull output, except that the crossover distortion is really extreme. Instead of being a 0.6 volt diode drop, it's a 2.5 volt V threshold offset. But you can see it follows with that enormous, ridiculous diode drop, the V threshold, quote-unquote diode drop, and then there's crossover distortion, and then it follows the upper half, and again this reaches 2.5 volts, whereas the input actually goes to 5 volts, and then here's another flat spot from crossover distortion. So that's kind of neat. I think if I make this much slower, this is a kilohertz, I haven't tried this, but I think if I go back and make this 100 hertz, and then if I go over here and I make this 10 times, so 3,000 microseconds per division instead of 300. Yeah, you see these spots are flatter. So if you rewind the video, you'll notice that the two spots were a little high and a little low. And I think that's a capacitive effect. I think that's gate capacitance, although I haven't tried to prove it. You know, if you wanted to prove it, you see, you could take a circuit lab model and you can see if you can reproduce it, and then you can actually artificially in the circuit lab model change the gate capacitance of the MOSFET. And you can see whether by dialing that physical parameter being simulated in the model, you can reproduce what you observe. So actually you could do some kind of neat physical modeling just by comparing your observations with a circuit lab simulation whose parameters you can tweak. But that's a digression. Anyway, so now you see this is a little more understandable because this is nice and flat at 0. So you have following the positive part, crossover distortion flat at 0, following the negative part, crossover distortion flat at 0. And these two channels are on the same scale, no offset. So you really do see this big offset here, this big offset here, which is the effect of V threshold. Now actually, so while I'm here, I actually do want to try powering it from plus or minus 9 volts. So I'm going to unplug the plus and minus power supplies. Here's a 9-volt battery. I'm going to wire from what used to be plus 5 to what used to be ground. Now this one I have to reverse the meaning of the red and the black. So this red is also ground, and now this one, because I'm plugging it in the other way, will end up being, so you see this is 9 volts between 0 and minus 9 volts. This is 9 volts between plus 9 volts and 0. So this black wire and this red wire are plugged into ground. This black wire is minus 9 volts, this red wire is plus 9 volts. Aha, so it didn't change anything, but it's sort of fun to see it powered from 9 volts, plus or minus 9 volts, instead of just plus or minus 5 volts. But in this case, it didn't make any difference. Okay, so that's the end of that video. So that was the CMOS push-pull follower lab20 part 2, which once again is hugely easier in Circuit Lab.